Yes. Okay, so we're recording now. Okay, yes, welcome everyone to this tutorial session on the optical modeling hands-on session. So first of all, I would like to acknowledge that I'm not the primary author of this hands-on session. That was Emil Bohr, who couldn't be here due to other reasons. So I took over and I helped finalize the notebooks. So the notebooks, they start with a bit of an introduction to the optical modeling software or the optical modeling package that we're going to use, which is called HCIPy, which stands for High Contrast Imaging in Python. And there are roughly three big topics, I would say, in this tutorial hands-on session. The first one is actually how do you work with HCIPy? What does it do and how does it work? Then the second is how do we model coronagraphs? And then the third session is aberrations and wavefront errors and how do they interact with your coronagraph and how do they change the performance of your coronagraph? So there's those three blocks that hopefully will be enough content. It should be more than enough for people to go through during the hands-on session. Yeah, so it starts off with just some standard Google Colab usage. And as I think the important thing is like is what's said here is that you should really read, and also when you're talking with people, just make sure that they really read what's written down in the cells. Like I try to add a lot of text to make sure that things are explained, and they shouldn't just blindly run everything. Right. Because in theory, you can run everything, get all the videos, but then you wouldn't learn anything.
Right.
Yeah, so the notebook starts off with installing HCIPy. And people can either, so I give people the option, either you install it on Google Colab, or if you're more savvy and you already know how Python works and you have an own installation, you can actually install it through pip. So this whole notebook can also run locally on your computer if you have installed the latest version of HCIPy through pip. I do recommend people to follow through on the Google Colab notebook, because then we're 100% sure that it works and that you can immediately just go and work with it. But it is possible for people to run it on their own machine too. And as far as I know, HCIPy should install on all laptops and machines that have Python 3 installed. I don't think we support Python 2 anymore. So if you have Python 3 installed, it works. We made sure that it's cross-platform, so it works on Windows, Mac, and Linux. Okay, so the first cell was just installing HCIPy, and then the second cell, well, let me just run the code, because then I can generate all the examples on the fly. Or let's see, no, they're already exported. So the installation takes a couple minutes, maybe a minute or two. So people just have to wait. That's also what I say in the text. So people just have to wait until it's installed. Also, if you have any questions, please just unmute yourself and then ask them. Then we can discuss them. Yeah, so then the first beginning, we're just importing all the libraries that we need. And this is everything. We don't need anything more than HCIPy, NumPy, Matplotlib, and this additional library TQDM, which is a library that makes a what do you call it, a progress bar. So that's just a thing to help us see the progress of simulations. So it's just easy to figure out how long everything takes. Okay, so in the beginning, it's really important for people to understand the HCIPy terminology. And I think this is also important for everybody that's now here as like a sort of as a TA, because HCIPy does things in a bit of a slightly different way than other optical modeling packages does. And the reason why we did this is because with this type of architecture, we can actually implement things like Fourier transforms very easily, and we can mix and match all these different types of basis transforms without losing things like energy conservation, without needing to re-implement specific sampling requirements. So there's a lot of numerical reasons why we've developed the code like this that makes it really powerful. So it starts off with this first block of code, and the goal is to have the participants understand this after the first part of this tutorial. So the first part is learning how HCIPy works, and so after the first part, they should be able to understand this whole code block, and they should be able to explain what each part does. So HCIPy, so this first code block, it creates a point spread function from a clear aperture, and it does it for different wavelengths. And then you run this cell, it creates a video, and you could already see there's this progress bar, and when it's complete, a video is made and you can actually run it. And here we can see the different wavelengths, or at least the wavelength scaling when we scan through wavelength. And because it's video, we can actually play back and forth. And I think this is something useful because the participants can then just move the button to the different wavelengths and just see how everything is impacted, like how the wavelength impacts PSF. And this is something that is done throughout the notebook, is that videos are made when we do parameter scans, so that it's really clear what a certain parameter does to the point spread function or the optical system. Okay, so the goal is to be able to understand this, and we understand. So the fundamental property that HCIPy works with, and that's the important thing to understand, is a thing called a field, which is a mathematical concept that originates from physics. And this field, because this is not a mathematical field, this is a physical field. A field is just any kind of quantity that varies with a spatial coordinate. So I try to give a couple of examples here. For example, a scalar field is temperature. Temperature is a scalar field. So if you move through your room or somewhere outside in the world at different spatial locations, you have a different temperature. If you have vector fields, then you have a vector component that changes with space. An example that I put in the notebook here is a river. And then the vector field is the velocity of the water parcels in that river, which are different for each position within the river. And then the third type of field is a tensor field, and that means that at every point in space, you have a different tensor. And then an example is the stress energy tensor for materials. So there's all these different types of fields. And you can make higher dimensional things, but as long as it's something that changes with space, it's a field. And that's the fundamental quantity that HCIPy works on, because everything in HCIPy is a field. Do you have transmission as function of coordinate in your pupil? That's a field. If you have a phase pattern as a function of space, that's a field. If you have a particular mode basis, then you can make a field, because a mode basis is nothing else than spatial patterns. So I hope that everybody understands what I mean with a field. And for fields, like I said, we have all these values, all these associated scalar fields, vector fields, tensor fields, they all have values, and each value depends on the spatial coordinates. And that means that the value and the coordinates are associated with each other. And that's also what we do in HCIPy. So we have a field and it consists of values, but also of grid points. So whenever you want to do something in HCIPy, you first need to define a grid on which you are defining all your fields. And you can have many different grids at the same time. So here I am defining a uniform grid, and a uniform grid is just a grid with a uniform sampling. So it's like a regular sampling between points. And in this case, it's 11 points in X and 11 points in Y. And then it's 1 meter wide and 2 meters tall. So this is a fundamental thing in HCIPy, which is different from NumPy, is that we are indexing X, Y, Z, and we're not indexing Y, X, Z like NumPy. So we swapped around the orientation of the columns and rows, and that's because people are usually more familiar with doing the X, Y, Z order if you're doing physics than the YXZ one that's caused by indexing of arrays. So that could be a thing where mistakes quickly happen. Okay, so then the second part is just showing that we can actually plot these type of coordinates. And then when you plot them, you can actually see all the points in the grid. So you can see all the X and Y points. So if we create a grid with 11 points in one direction, 11 points in the other direction, we get 121 in total because it's 11 by 11. But this function is difficult to use. Well, it's not difficult. It's a little bit inconvenient to use because you need to specify the number of points in each dimension and the size of each dimension every time. So we made a couple convenience functions for planes that often happen. So for example, the pupil plane is a plane that you very often simulate because we're doing Fourier optics and coronagraphs, and that means pupil planes are like the basic thing. So instead of making the uniform grid, we have to make pupil grid function that just makes it easier, where it's just the number of pixels and the physical size of the grid. So there's only 2 numbers now instead of making 1 for each dimension. So this is just a convenience function. And we have the same thing for the focal plane. However, the focal plane is a little bit more complicated. So if we run the documentation line, we can actually get the documentation for the focal grid and figure out what the parameters are. Now, this function was created at the time when we had a different interface design for HCIPy. And because of that, because of backwards compatibility, we still kept a lot of the older parameters that you can pass to the function so that we don't break people's code that depended on an older interface. And this is something that I also say in the code itself, but people should not use all the parameters. They should only use the parameters that I really specified here in bold, because that's the parameters that you use for the new interface. So if things don't work when they call this function and they accidentally use some of the other parameters, then they should probably switch back. So in this focal grid function, you can make it for whenever you need to do something in the focal plane. And the reason why we made this one different is because we want to make it easy to define the number of pixels in your focal plane and the size of your focal plane and the spatial resolution. So those 3 things are things you usually know about your focal plane. So that's why we specified them in the interface. Everything outside this very specific thing about parameters It's not really necessary to know. Okay, so those are the easy helper functions for making grids. Now we want to create fields and figure out how to work with fields. So here, the first thing that we do is we make a pupil grid because we want to define a circle in the pupil, so a clear aperture. I make it 128 pixels, and I give it a physical size of 1.1 meters. So when I create the circle, we need to get access to the coordinates because we want to get the radial coordinates. And here I show how you can actually index and access the X and Y coordinates of your grids. And well, if you have an X and a Y coordinate, it's very obvious how you calculate the radius. It's just Pythagoras. It's just X squared plus Y squared. You take the square root and then you have R. And then if we want to make a mask of a certain size, we just say that the radius should be smaller than that diameter divided by 2. And then this is the important part where we make a field, is that if you want to make a field, the first quantity are the values, and the second quantity is the grid that's associated with those values. That's how you make a field. So this is just a very basic code to show people how to work with fields and how you can create a field. And we can actually show that it works with this circle. We just made a circle. Okay, is everything clear up to here, or are there questions? Okay, because there are no questions, I assume that everything is clear. So let's continue. Wait, how do I get rid of this? Okay. So this circle function is great. We just made a circle function, but HCIPy has that, of course, natively implemented, and the function from HCIPy itself is better. So we should just use that. This function is just there to show people how you can actually access the coordinates in a grid and how you can make fields. So this is just to show the nuts and bolts of HCIPy. But in principle, they should use native implemented functions if those are available. Okay, so then another pitfall of HCIPy, which is important to understand, is that HCIPy has a lot of things that are called function generators. And a function generator is a function that returns another function. And that's where this part of the code focuses on. So this line where I show the tutorial aperture with HCIPy make circular aperture, this returns a function. So this make circular aperture is a function generator. And the reason why we do that is because we want to make an arbitrary concept of a circular aperture. So this function that it returns can be evaluated on whatever grid you specify. So now we have a function that creates circles, but we need to evaluate that circle on a certain grid. And here I show that we can make a low resolution grid, and we get a low resolution pupil, and then here we make a high resolution pupil. And as you can see, we are using the same aperture. We just use different grids to evaluate that aperture. And that creates the different samplings of, on the left, the low resolution pupil, and on the right, the high resolution pupil. And we did it in this way because with these type of function generators, it becomes actually very easy to switch resolution or to reuse the function itself. Does anyone have a question about function generators? No, good. Then I'll continue. So those are the fundamental quantities of HCIPy, grids and fields. And a field is nothing else than a set of values that are associated with grid points. And another important thing to know is that these fields, you can operate on them just like you would do with NumPy arrays. So that's also important to know. They're just, for most purposes, they just act like NumPy arrays. For example, here we can actually multiply it by 2, like how you would do in a NumPy array. And then it actually becomes twice as big. Or you can add a number, or you can add like a number to it, and then it adds that number on top of it. Or we can actually take the square root with a NumPy array. I mean, the square root of 1 is just 1, so you won't see any difference here. But I just want to make sure that everybody understands that these things, we call them fields, but they just operate like NumPy arrays. You work with them like they are a NumPy array. Okay, so if we have this under control, the fields and the grids, we actually go to wavefronts and optical elements. So the highest type of software element in HCIPy is a wavefront. And a wavefront is a thing that you propagate through an optical system. And in HCIPy, a wavefront consists of an electric field, which is a field object, like all the field that we just discussed. The wavefront also has a wavelength. It has a polarization state, and it has a total power. So that's the number of photons. So we can look at the documentation and we can actually read all the parameters that are necessary to put in the wavefront. So the minimum amount of parameters that you need to specify is the electric field. If you only specify the electric field, and this is for all this important for the TAs, then it assumes that the wavelength is 1, that the light is completely unpolarized. So you have a Stokes vector that is 1, 0, 0, 0. It assumes it derives the photon count from the electric field that you supply, and the total photons is just the sum of the intensity that comes from the electric field. And I think that's about it. So in theory, the minimum amount of things that you need to give to a wavefront is an electric field, and then the rest will follow. So these wavefronts, those are the elements that we actually interact with. So all the optical elements, all the optics that are implemented in HCIPy, they operate on wavefronts. A wavefront comes in and a wavefront goes out. That's how an optical element is implemented. So whenever we have something that interacts with a wavefront, it's an optical element. And with an optical element, we also mean something that can be very abstract. So very obvious things are things like a transmission filter, a polarizer, or a lens. However, you can also have more abstract types of optical elements like a propagation. Like if the electric field moves from one plane to another plane, then that's also a optical element because a wavefront comes in and a wavefront goes out. So we can make propagators, for example, a Fraunhofer propagator. This propagator takes a wavefront that's defined in a pupil and it propagates it to a focal plane. So that's useful when we want to look at things like PSFs. So this is the summary of HCIPy terminology. There are several more tutorials on the HCIPy website that you can refer to, where you can refer the participants to. But I think this is enough for this tutorial. Okay, before I continue, again, are there any questions or is everything clear? So I guess either everything is super clear or I'm overwhelming everyone. Because there are no questions, but that's okay. Okay, then I will just continue. So the second part of the introduction is to learn how to create a PSF. Or now after we've done everything, people should be able to go back. And maybe I'll add that as one block, that people should go back to this code block and see if they understand everything that's done to generate the PSF. So now we should be able to explain everything that we see here. And with that information, we can actually start making PSFs. So in the introduction lectures, people learn about apertures and how each aperture generates a different PSF. So that's also what we start with. We will start with creating different PSFs. For example, if we run this code, we can actually see what changing the central obscuration does. So we can see that it's creating different PSF. And I think this is a part where we should just let the participants play a little bit, where they can look through the videos. And in principle, and in theory, it's also fine if they change the parameters of these simulations. Because the goal here is for them to learn and understand how different types of geometry or modifications of your pupil, how they impact your PSF. So what we focused on in the beginning is central obscuration, spiders, the thickness of the spider, and how those change your PSFs. And after that, we start with some questions. And the majority of the exercises in this notebook are actually explain questions. The reason why I chose to do that is that coding things up takes a while, and it's very easy to make mistakes in coding. And I think it's more useful for people to see things like changing the PSF or changing like how the aperture, like if you change the aperture and see what PSF becomes, and then being able to explain these simulations, I think is probably more important than being able to code it up. Of course, this is a hands-on session, so people are allowed to code things and change things. But if we want to make sure that everything is contained within the time that we have, it's actually a little bit difficult. So I would say that probably the majority of, like, if people really want to code, it should be done during the group project. That's where they have more freedom. So in the first part, we need to explain what we see and what changing the parameters does. So here I was a little bit confused. Maybe Tracy could explain to me, should I make a separate notebook where I explain the answers for all the questions?
Yes.
Okay.
Yeah, we have for the other two training project group, other two hands-on sessions, we do have separate answer sheets for the answer notebook for the helpers.
Okay. Then I will make that one too. Yeah. Yeah, so they need to explain exactly what happens when, or at least they need to critically look at the simulations here, and they need to explain what they see happening based on the physics they were taught by the lectures from the first day. And I think that that should be doable. It might be a little bit complicated, but if you want to go into the details of it, but I think generally they should be able to explain it. But if they, I'm not So yeah, so the goal for this is really that they should be able to explain it qualitatively. Quantitatively, it's more difficult to explain because then they need to understand the mathematics of Fourier transforms quite well, which might not be a problem for a lot of people. But maybe for some it might be more difficult because they're not super familiar with all the mathematical properties of the Fourier transform. So the goal is to make sure that people have a qualitative understanding of the behavior. So I will make an answer sheet for these questions. And then people here can also look at those answers. I don't know if people already had time to go through the notebook before this session. If someone was already able to go through the notebook and look at it, I was wondering what you were thinking, what maybe the thoughts are on the questions, and if you think that they are too difficult or if they're not too difficult, especially here in the beginning.
Just a reminder, we also have a hands-on helpers Slack channel. So
Yeah.
if you have any questions, you have any feedback for the notebooks, feel free to post it on that channel.
Okay. So after we've done simple apertures, because these are simple apertures, we actually go to, we want to show the PSF of more complicated apertures, which are shown here. So these are the apertures for all the, let's close this, for the more realistic telescopes. And we have implemented quite a lot of different telescopes in HCIPy. We have not implemented all the telescopes on Earth, but I think we're very close. But these are all the most important telescopes. And you can really see, I think, what is really important here for the participants to see is figure out like, oh, I see a certain symmetry in the aperture on the left, and you can see the similar symmetry on the right in the PSF. For example, in this one, it's very clear. We have the GMT aperture, and we see 6 petals, and that means there's a 6-fold symmetry, and that's also something that you see back in the PSF. If you go to TMT, the TMT is more circular because it's all small segments. So you can see the main structure is circular, but then at high frequencies, we see the spiders have a 6-fold symmetry again, and that's because of the 6-fold symmetry of spiders. So that's something that people might want to explain. Okay, so after we understand how propagation from wavefronts from an aperture to a focal plane works, we will go to coronagraphs. So in coronagraphs, we start with the vortex coronagraph because the vortex coronagraph works and is perfect for clear apertures. I did not want to do coronagraphs for complex apertures because that's more confusing. We'll just start with a vortex coronagraph. So first, I'm going to show the vortex coronagraph focal plane mask, which shows why this thing is called a vortex, because you can see here we make a vortex pattern. So, and then the next step is to actually make the vortex code. So, and they should know the general layout of Leo stop now, of a Leo coronagraph, where we have an entrance aperture, a focal plane mask, and a Leo stop, because that was part of one of the introduction lectures. So if they don't understand the optical layout, they should refer back to the lecture slides. And the lecture slides are always available too, right? After the lecture has been given. Okay. So we've just made all the apertures. We made the entrance aperture, we made focal plane aperture, we made the Leo stop, and then we created the vortex coronagraph with this part of the code. And then we can actually show what all the different parts look like. We have the pupil, the focal plane mask, and the Leo stop. And as you can see, the Leo stop looks very much like the pupil, and that's because it's just slightly undersized by 5%. So we should not expect a dramatic difference between the pupil and the Leo stop. If there's a dramatic difference, then someone has messed up their notebook. That's something they put in different parameters. So if we just propagate the waveform to the focal plane, we should get a normal PSF, because this is the PSF for a circular aperture. And then we go through the vortex coronagraph. An important thing to note for coronagraphs in general in HCIPy is that they propagate through the vortex, through the coronagraph and back to the Leo plane again. Some coronagraphs have numerical issues, and because of that, you need to treat them in a very specific way to make sure that you can circumvent the numerical issues. For example, a problem with the vortex mask is that in the center, it's really undefined what your phase should be, because it, as you can see, it wraps around. But if you make the circle smaller and smaller, then this wrapping happens quicker and quicker and quicker. And when you're exactly at the center, then it's really undefined what the mask does. But due to finite sampling, we don't sample this singularity with high enough resolution. And because of that, you can very easily generate numerical artifacts that are at a contrast level of like 10 to the minus 6 or 10 to the minus 7. And then the participant, then if you just naively would implement a vortex chronograph, you would think it doesn't work well. While the vortex works perfectly well, it's just your implementation of the numerical propagation is wrong. So we have done special things in HCIPy to actually handle those type of numerical issues. And because of that, it will never do just a simple propagation from the pupil to the focal plane and then back to the pupil. It does a more complicated transform to make sure that we can handle these artifacts. That's what I explain here. And the output of the vortex, or the input, then should be the entrance aperture, and it should not be an electric field in the focal plane. It's the entrance aperture electric field or wavefront that needs to be propagated. So that's why we also start with a wavefront in the pupil, and that is what gets fed into the vortex coronagraph. And after that, we need to apply the Leo stop. And then finally, we can go to a focal plane again and get our science image out. This image that I make here, this wavefront here, is just to create a reference PSF. So we have the PSF without the coronagraph. We have the PSF, or the final image, with the coronagraph in. Let's see, and then and we made a convenience function to show all the different planes in the vortex coronagraph. So what this function does, you just give it a wavefront, and then it will propagate that wavefront through the vortex coronagraph and through everything what we just did, and it also plots all the power at all the different planes. So if we show this, then it takes a minute, but then you can see we have the entrance pupil, we have the PSF at the focal plane mask, we have the light at the Leo stop, we have the Leo stop, we have the light after Leo stop, and we have the final image at the science camera. So, and these are then the images that the participants will use to understand the behavior of the vortex coronagraph. Now we can also make an off-axis source. An off-axis source is made by having applying your aperture or your pupil together with a tilt. And here we tilt the source by 1.5 lambda over d. And if we do that, then we can see that the PSF actually has shifted. It's not centered on the center of the plane anymore, and it goes through the system, and we can actually see it at the final image. It's not perfectly nulled, and that's what we want for a chronograph. something that removes everything that's on axis, but passes through everything that's off axis. Okay, so this is the basic function they will use. And here I'm asking them how to create a couple animations and also ask them to understand what's happening at these images. So I made a couple questions that I think everybody should work on. And then there's a couple bonus questions. So because there are going to be people that are fast and understand everything already. And there are people for who this is completely new. So I sometimes add bonus questions in between for the people that are faster, so that they also have something to think about while other people are working. So the bonus questions are not for the group project or anything like that. This is just for people that are fast. Let's see. So for this one, we do have the solution. Yeah. So we have part of the problems are already solved, and we have them here. But this is something that we want the participants to work on for themselves. And it doesn't really matter how they make the animation. For example, here, I'm actually using all the helper functions that we use in this notebook to actually make it easy to make a figure or to make an animation. As you can see, it's only a couple of lines of code. But probably for the majority of people, this will be like magic. So they'll probably try to implement their own video code based on the helper function that's defined here in one of the first cells. And that's fine. That's okay. For the people that understand how that helper function works, they can probably do it very quickly in these couple lines of code. For the other people, they might come up with something else, but that's fine. The goal in the end is for people to understand how to apply different off-axis angles, like how they shift the PSF and how they propagate it, and how they can create PSFs at different positions. And this is roughly what it should look like, where you can see that PSF moves to the right, and then PSFs at the right are passed through, while if we're in the center, more towards the center, they should see a lot of nulling, which is what the coronagraph does. Okay, so after passing through the coronagraph, we need to start analyzing its performance. And one of the performance metric of a coronagraph is the throughput of an off-axis companion. So the next part of this notebook will be to measure the throughput. And first, we need to define how you measure throughput at all. And what I have chosen is to create a photometric aperture that's centered on the position of your companion. So if the companion is at 10 lambda over d, then the photometric aperture is also at 10 lambda over d, and it has a size of 2 lambda over d in diameter. So it goes from 1 lambda over d in radius. Yeah, it has a 1 lambda over d radius. And here I made an image of how that looks like. So we see the PSF together with the size of the photometric aperture. So effectively, we are just measuring all the light that's in the core of the PSF and nothing in the rings. And that's okay. We should be able to capture about 80% or so of the light in the core. So after we have defined our aperture, we can actually measure the throughput. So we can measure how much light goes through for different angles. And then we get this nice figure. And now we can actually measure the core throughput as function of angular separation for a companion. And then the things that they should understand is that if you're very close to the star, there's very little throughput. So you have very bad sensitivity. While if you're far out, there's a large amount of throughput and you have high sensitivity. So you can really search for planets. So, and again, we have a couple questions where the first two questions are qualitative questions where people are, the first is qualitative, and then the other three, there is a little bit of coding involved, and that will be mainly copy pasting of the code that we just made. So the main thing that you need to do is to compute the inner working angle, which is defined as the position when the throughput reaches half the maximum core throughput. And they might need some help with question 3, because for questions, if you want to do question 3 correctly, you need to know the answer to question 2. So if they are not able to get question 2, they won't be able to get question 3. So there's a little bit of dependency between those two. But in principle, it should be the answer should be very close if they just look at this figure, because you can for question 2 they need to compute the maximum core throughput, which is the throughput at infinite angular separation angle, and that means if you separate the PSF by a huge angle, what's throughput? You can already see in this figure that it sort of converges to something to a little bit above 70%. So if they take this number at 10 lambda over d and then use that as the reference value, then that's also fine when they use that to compute the inner working angle. I mean, it's not going to be the exact numerical precise inner working angle, but it will probably be good enough. Yeah, and then the second thing is understanding that the vortex coronagraphs works really well for clear apertures, but real telescopes are not clear apertures. So in this part of the code, they can play with different apertures and see how the performance of the coronagraph, of the vortex coronagraph, changes with that aperture. Okay, so this is the part about coronagraphs. Let's see, I thought. Okay, yes. So this is the end of the coronagraph section, or at least the basic coronagraph behavior section. And then we get to the third and final section. So this third and final section talks about aberrations and coronography. So the goal here is to show participants how aberrations impact your coronographic performance. And we start with discussing how coronagraphs work at all, or how what aberrations do, just in the perfect case. So we start with science. Yeah? Is there a question?
Sebastiaan, there are a couple of questions in the chat. I don't know if you can see that.
No. Okay. Yes. Oh yeah. Okay, so let's see, Yamila, is that correct? Your name? Yamila or Jamila, I don't know. You're asking if said it's difficult to describe some of the effects. Yeah, okay, thanks. Yeah, so here about the qualitative explanation of the PSF. So So I think what you're meaning is, well, what you're saying is correct, exactly. So, for example, a spider is a rectangle, and you're subtracting it from the PSF. That's correct, and that means that it creates your original PSF minus a Fourier transform of a rectangle, which is a sinc pattern. And if you make the sinc pattern, you get actually the interference effect of the two. So that's sort of what you're seeing here at the larger end, is that here you can see these gaps, which are created by the nulls, the first nulls of the sinc pattern. And I think that's qualitative enough for people to understand it. For example, here, what I want to say is that we see a certain number of spiders in the pupil, and that means we also see a certain number of stripes in the focal plane. However, there is also an issue with symmetry. So if we have one spider or two spiders, why is the pattern, what is the difference between applying one spider and two spiders? That's a more difficult question to answer. But qualitatively saying we have a thin spider, and that means it creates a thick structure in the thin direction and a small structure in the broad direction. That's sort of the qualitative things that I expect people to know. So the basic thing is big things in the pupil are small things in the focal plane. That's sort of the qualitative thing that they will need to know. Good. Yeah, so as you said, like the exact numerical details are complicated. And for that, it's easier to do the Fourier transform with a computer. But just qualitatively, they need to understand, like, oh, if I apply a stripe, it Fourier transforms into a stripe, and it interferes. Okay, good. Okay, I'll try and keep my eye on the chat now. Okay, let's go back to where we are in the tutorial. Yeah, we were talking about aberrations. So I started with very simple phase sinusoidal aberration, because the sinusoidal aberration creates 2 points. And that is also the goal of this first video, is we're making speckles. And then I'm asking people, like, how do we expect these points to change when we modify the parameters of the aberration? So if we increase the amplitude, we can see that the first thing that happens is that the off-axis spots become brighter. But if we make it really strong, then we can also see that there are second order spots that are generated. So, and that's an effect of the nonlinearity of phase aberrations. Because if you make phase aberrations really big, they create a nonlinear effect on the focal plane. While if you're in the small phase aberration regime, we just have we can make a linear approximation, and then we only see 2 points. And then for the position, of course, we change frequency, and if we change frequency, then the speckles move out, because high frequencies correspond to things far away from the center. And then the third one, phase, which is more complicated. What happens if we change the phase is that this sinusoid changes from a sinus into a cosine, and a cosine has slightly different behavior than a sinusoid. And that's also why the interference pattern changes here and here in between, and then here again, and at the end it's different. So this is just mainly a difference between a cosine and a sine, which have different symmetries and therefore different interference effects. So that's I mean, we are asking people, like, what they do. But this is that's why explaining this, like the difference between a cosine and a sine and their symmetries, That's a complicated question, and that's why it's a bonus question. That's why we keep it qualitatively again, and that means that bigger amplitude means brighter speckles. Changing the frequency means the speckles move out or they move in, depending on if you make it bigger or smaller. And the phase parameter changes the way that Fourier sinusoids interfere in the focal plane. Okay, so after we've done sinusoidal speckles, we move on to more complicated speckle aberrations, and those are Zernike aberrations. And the first set are just low-order Zernikes, which are usually related to instrumental alignment errors. So for example, if you misalign your optics, or you have small thermal drifts inside your system that moves the optics, then these are the aberrations that appear. And these are also then the most important ones to really understand, because these impact your performance quite a bit. So we start with just showing the phase aberrations and how they look like the different Zernike modes. And then we go through this part of the code that actually generates the sensitivity. Ugh. Why? I thought everything was working when I ran it yesterday. That's because I have not executed a lot of the, I just skipped running. I didn't run all the cells. That's why it didn't work. Okay. So this part of the code takes quite a while to run because it does many propagations. Or wait, it's the next one that takes a while. So here we see the different modes or the different phase modes and how they propagate through different vortex coronagraphs with different charges. So charge 2, which is the smallest charge, and charge 10, which is a really big charge. You can see that if you increase the charge, you actually increase the rejection of the chronograph. So it can reject more modes and more aberrations. So high order means we can filter out a lot of modes. Low order means we don't filter a lot of modes. And that's something that we can then also see in these simulations where we actually inject different amplitudes. Let's see, this is running. Yes, and then we have the final couple of questions where people need to explain the difference in behavior. Like how are the different chronographs or the different charges of the vortex related to its behavior against these low-order aberrations. And they should be able to explain that if they look at the graphs that this part of the code generates and the figure here that's generated by the previous block. So they should combine the information from the different blocks to come to an answer. So they don't have to explain quantitatively what happens, because that's a lot of difficult mathematics, but they should be able to qualitatively explain that a charge 2 vortex is sensitive to a lot of aberrations, because you can see they leak through. And that means it also, a low amount of aberrations already creates a lot of leakage, while a high order charge 10 vortex chronograph, it takes a really long time before the aberrations leak into the chronograph. And that means that we're more robust against wavefront aberrations. Yeah, it takes a while for this figure to be generated. So I need to wait a minute and then I can show what I mean. Let's see how many iterations. Okay, so it needs to do 15 iterations. So another 4. So this first set of simulations is done for a charge 6 coronagraph, or charge 6 vortex coronagraph. And a charge 6, which is this one, you can see it filters the first 4 modes, and then it passes through higher order modes. And what we would expect from these simulations then is that it's robust against these first 4 modes. So those should appear much later if we inject them in the contrast. And that's also what we see here. So now we have a set of modes, and then the first 4, they appear on the right side, where on the x-axis we have aberration strength, and on the y-axis we have leakage, or like how much the contrast changes after your coronagraph. And we can see that for these first 4 modes, we need to inject them with a relatively high strength. That's like 1,000 times higher than all the other modes to get a similar amount of starlight. So we're 1,000 times more robust against these 4 modes than the other set of modes. And that's sort of qualitatively what people need to be able to explain. And they can change the charge. So they can go to a charge 2 or a charge 10 or a charge 4 vortex coronagraph. And then they can see how the modes switch to sensitive mode group and robust mode group. And after that, they have sort of finished the tutorial. So this is the end of the tutorial, and I added an advanced topic, which I first added for people that are extremely fast and they wanted to do something else. But I think it's also very nice as a group project where I can actually, where I set them up with an adaptive optic system. So until now, we have mainly done coronagraphs for space-based telescopes because there's no atmosphere, there's no turbulence. But when you add atmosphere and turbulence, then coronagraph behavior becomes slightly different. So in this advanced topic, we're actually making turbulence. So here you can see a wavefront that's moving. This is turbulence. And then when we go through the atmosphere, you can actually see that this is the PSF if we don't do any adaptive optics, and it's just a lot of speckles. So we do some adaptive optics, and then we can actually generate nice PSFs. And we can also generate the coronagraphic PSFs on the right. So we have PSFs, coronagraphic images, and then the bottom ones are long-term images. So those are the averaged images over time. And then there's a couple of advanced questions that they can start to answer. And I think these are good for a group project. Okay, so I guess I'm through to the end of my notebook. Are there any questions, comments, suggestions? I'm happy to hear some feedback. Or if you have questions about the notebook itself. Okay, I guess not. So I guess everybody's really excited to hop off.
Okay. Yeah, I don't see any more questions in the chat. So I think that would be it for today. Again, thank you, Sebastiaan. Especially like given such short time you had to work finishing this notebook. Thank you very much. And then as Sebastiaan mentioned, he will be preparing the answer notebook for the group projects. So we will post that in the hands-on helpers channel, and we'll also send email out to the whole email list. Please review the notebook, test them, and if you have any questions, ask away in the Slack channel. Sebastiaan can help you there. I think that would be it. Thank you everybody for attending this morning's training session.